construction of the diffusion coefficient of the QGP, and basically the prior uncertainty is the gray band, and the uncertainty that you have on the dependence of the diffusion coefficient of the quark-gluon plasma on the temperature is shown by the red area. As you see, we are not yet to the top of the precision, but we are really getting there, and this will reduce spectacularly in the coming 3 to 6 years, as you will see. A very important observable in the study of quark-gluon plasma is the suppression of the production of J-psi. This is one of the original signatures of the QGP phase transition that was predicted in the 80s. And what is shown here on the left-hand side is the centrality dependence. So in number of participants, more central is on the right, less central is on the left. And what you see are the data from the Phoenix experiment at Rick in black, and then the colored points are the points from ALISA, two different energies. And as you can see, the centrality dependence is very different. There is less suppression, first of all, and if you look at the PD dependence, which is shown on the right, you see that it's very different, essentially opposite than the one that is observed at lower energies at Rick. And the natural explanation for this is that at the LHC energy, you have a large number of CC bar quarks which are produced in each collision, and therefore you can have a new mechanism which you don't have at lower energy, which is not important, let's say, at lower energies, which is the production of J-psi by recombination of quarks from the quark-gluon plasma. This is the azimuthal asymmetry of the J-psi production. By now we have over 5 sigma evidence for this. And why is this important? To know that the J-psi has an azimuthal asymmetry. Because we know that charm quarks originally are produced isotropically, so there is no anisotropy in the direction, in the original direction that charm quarks are produced. It's completely random. So the fact that you have one appearing in the J-psi which contains only charm quarks, no light quarks, then it's a clear indication that the charm quarks are coupled very strongly with the quark. And we can measure many fine details and actually observe new phenomena in the QGP, which is what makes this physics so interesting. And this is just one example. This is spin alignment in the quark-gluon plasma. Basically, in non-central collisions, you have very large angular momentum. The QGP rotates. There are estimated to be about 10 to the 21 revolutions per second, and at that point spin-orbit interaction can polarize the quarks. And then, if you want to build a vector mesons, if you build it by recombination of these polarized quarks, you will get spin alignment. And this seems to be what we observe, at least at 3 sigma level, for the production of K star 0. These are the red points, rho 0, 0 as a function of transverse momentum, whereas for the control K 0 short, where of course you don't expect anything, you see that the measurement is flat. And why is this important? Because this gives us a direct window on hadron formation and on the transport of angular momentum inside it. And you will hear much more about this measurement in the talk by Bedanga on Thursday. Now, one of the main surprises at the LHC was the detection of collective effects in small systems. I will not go into the details of this particular measurement because it's a tricky one in the interest of brevity, but essentially there is a clear two-component structure. If you look on the right, you have delta eta on the upward right going axis, and you have delta phi on the upward left, and you have delta phi on the upward right going, and you see that you get clearly two ridges, one on the near side and one on the away side. This is after all jet contributions have been subtracted, and this is a clear indication of a V2-like behavior, so of an original azimuthal asymmetry in the soft particle product. And this is what is normally associated to the expansion of the quark-gluon plasma, as I showed you a few slides ago. And what is very striking is that if you look at these two figures, essentially what you have on the left-hand side, this is the behavior of V2 for identified particles, for different types of particles. And you have a clear hierarchy at low transverse momentum, whereby you have the effect is lower and lower for higher and higher momentum particles. And this is a direct translation of the transverse expansion of the system. So if you have a uniform velocity field, this acts differently on particles which have a different mass. And very strikingly, you find essentially the same pattern that was observed in lead-lead collisions. So somehow all the boxes are checked, and it seems that really we have to do also in proton-lead and in proton-proton collisions at high multiplicity with a transverse expansion at very high velocity. And then there was the measurement of strangeness enhancement in small system collision. This was another one of the hallmarks of QGP. It was observed in the 90s already at the SPS, and now we observe it in high multiplicity proton-lead and proton-proton collisions. It's not reproduced by the standard event generator models, and we don't know what it is yet. It could be the presence of QGP in small systems. It could be some sort of precursor phenomenon, but certainly it's pointing out new directions for research. This is a collection of the data, and what you see is, as a function of the particle multiplicity, you see the ratio of the yield of different types of particles to the yields of pions. And there are many different systems on this slide. You have lead-lead, but you also have proton-proton, proton-lead, xenon-xenon. And you see the systematics is very clear. It seems to depend only on the multiplicity of the collision, not really on the collision type. And this is very striking. And of course, it's a challenge for event generator. By the way, as an aside, this could help resolve the muon puzzle in cosmic rays, because if when you hit a nucleus, you have an enhanced production of strangeness, one can go, and is shown in some of these papers, very close to reproducing the ratios of muons, because basically, if you have more strangeness, you have more chaos, and the ratio of muons to pions in chaos decay in chaos decays goes exactly in the direction and almost totally quantitatively to tackle them. Where most of the estimates normally are made with minimum bias protocol. And no sign of quenching yet, of course. We know that we associate the production of a quark-gluon plasma to the quenching of high-energy partons and therefore high-energy hadrons, but this is one of the latest results. These are pi zeros out to 200 GeV in PT, and you see that there is no sign of that. Of course, we know that the highest, let's say the most visible effects of QGP-like effects, let's call them, are in high multiplicity collisions. This is minimum bias. doing this restricted to high multiplicity collisions is tricky because there are a lot of biases to correctly determine in this type of small system collisions exactly the number of colliding nuclei. So, but we are after this. So I think that people are getting more and more clever. So I think we have to stay tuned for this because on the other hand, the effects, if they are there, could be small, so small that we have not detected them yet. So we'll wait and see. And now I will go very quickly to the let's see how am I doing on time. Well, almost there. So to our platform. So this is the timeline of the LHC. So we are here in 2022, sorry, at the start of what we call Run 3. And then we have a plan which is laid out until the late 30s. And during the long shutdown 2, which has just concluded, there were important upgrades to the LHC, also as a heavy ion collider, and there was a major campaign of upgrades of the ALICE experiment. So, what are our physics goals? Basically, we want to zoom in a few particular areas. One is the study of heavy-quark interaction in the QCD medium. As I said before, this is one of our main workhorses. It really allows us to get down to the very quantitative level and also to observe very fine-grained phenomena in the QGP. We want to study charmonium regeneration, again down to 0 PT, which is where most of the interesting physics happens. We want to study chiral symmetry restoration and the radiation of QGP, so vector mesons and photons, virtual and real, and the production of nuclei. I will not go into many details, but to do something like this, you need very high precision. So we have a new vertex detector, which is totally made of pixels, and then you need high statistics. So we have a high-speed TBC, which is where we have replaced the readout planes, which were made with multi-wire proportional chambers with gem chambers, and now we target the 50 kilohertz minimum bias rate in that level. These are just some pictures of the silicon pixel detector that we have just installed, 10 square meters. This is the largest pixel detector in the world. The pixel pitch is about 30 by 30 square microns. This is just a picture of the TBC. Unfortunately, I have been asked to be fast, so I will not go into many details. Let me just tell you that these are 4 gem stacks for those who are interested in these things, and we managed to suppress the ion backflow to less than 1%. And of course, you need to read out all this, and you need to resolve the pileup in lead events. And we have about 5 events which pile up in the TBC at any given time, so we need to go to continuous readout. The data size is humongous. We start with about 3.4 terabytes per second, which we have to compress down to something of the order of 100 gigabytes per second, or a little bit more. And of course, to do this, you need a computer center, and we have installed a computer center right at point 2 that takes care of all of this online. We are essentially triggerless. And for the future, we are getting more and more ambitious. First of all, for long shutdown 3, we are targeting a forward calorimeter that will allow us to really go push as far as possible down to in X the study of the nuclear modification of the Parton distribution function. And for later still, we want to really try to push the detection of heavy flavor to its maximum at the LHC. And in order to do that, you need to go as close as allowed by the machine to the primary vertex. Also, we are now at the maximum rate for a TPC. So in order to go to the next level, beyond the 50 kilohertz, we need to change the technology from TPC to silicon again. So what we are doing, we are essentially building a huge pixel detector, huge in terms of pixel detectors, but small in terms of overall size for a tracker. And this is what we call ALICE 3, the next generation of ion experiment at the LHC. It's essentially an all-silicon tracker, wide rapidity acceptance, 8 units, with a high resolution vertex detector, superconducting magnet system, identification of hadrons, muons, and electrons, electromagnetic calorimeter, and a forward conversion tracker. We want to measure heavy flavor hadrons down to 0 pt, dileptons essentially down to 100 MeV, photons down to 100 MeV as well, and quarkonia and exotica with muon identification and central rapidity down to pt equals 0, which is not possible at the moment. We have to go a bit forward to do that. Jets, ultra soft photons, we have a dedicated conversion tracker that should allow us to go down to a pt of 1 MeV, and nuclei, of course, at high temperature. I will skip this, but I want to show you how we plan to go as close as possible. First of all, you have to use, sorry, I skipped that. First of all, you have to use silicon that you can bend, because then you eliminate all the material. The silicon essentially supports itself. So we are very aggressively developing, together with the industry, silicon wafers that can be bent and that can still have full functionality. And then, in order to go as close as possible to the primary vertex, you have to go inside the beam pipe of the LHC. And this is an animation of the system that we are looking for. These are, of course, only the 3 inner layers. So the problem is that you can go, the closest that you can go is 5 millimeters. But you cannot go there at injection, so you need to have a mobile system that goes out to as close as is allowed at the injection of the LHC beam, which is 16 millimeters, and then that closes on itself 5 millimeters when the stable beams are declared. And basically, this is the kind of movement that the system has to make. So there is a central barrel and an end cap region, and they have to move together in this way. This is called iris, because it moves a bit like the iris of the eye. And this is another view of how the system will open and close in order to allow to go really down to 5 millimeters, which couldn't be allowed when they inject the LHC beams. Now, just to conclude, a few words about the physics potential. We want to measure multi-heavy flavor hadrons, psi CC, omega CC, omega CCC. These essentially are these are hugely suppressed in standard production, so they can essentially only be produced by recombination of quarks. And this gives us the possibility of having a direct access to the recombination of our probe quarks, which are the chunk quarks in this case, and it allows us to have a huge sensitivity to even very small, tiny deviations from equilibrium. So it's a very sensitive probe of equilibrium. D-bar correlations, of course, over a very large rapidity acceptance, B mesons down to essentially 0 PT, Chi-C, but also the exotic XYZ state. With low mass dielectrons, we should really be able then to go down to the thermal continuum with virtual photons to study the fluctuations of conserved charges, which are very sensitive to deviations from full equilibriums and to the behavior of the system close to equilibrium, to thermodynamic equilibrium. Ultra soft photons, as I said, nuclei and hypernuclei. But more generally, this will be a unique experiment at the LHC with capabilities which are very complementary to those of the other LHC experiment, and it will be a very precious tool to really try to extract from the LHC all the physics that we can possibly extract by combining the measurements from all the experiments. It will help us, for instance, in beyond standard model searches. It will be competitive for the dark photons, very competitive for the search of axion-like particles. We are also looking at the high precision measurement of the G-2 of the tau, etc., etc. And we will install, in the next shutdown, we will install a sort of prototype of this that we call ITS3. Now, to my conclusions. With high energy accelerators, as I showed you, we can recreate for a tiny instant in the laboratory the QCD plasma. This gives us a direct window on collectivity with fundamental constituents. By the way, this is the only phase transition in quantum field theory that is experimentally accessible. At the LHC, we have ideal conditions for doing this, high statistics, calibrated probes, and essentially a very large baryon-free central region. The particle yields appear to be thermalized into Stranger's enhancement. The pressure gradients, which are built as the QGP expands, result in an explosive expansion at about 2/3 of the speed of light. We have almost ideal fluid behavior. High energy partons are strongly quenched, and this provides us with a very precious tool to essentially perform a sort of Rutherford experiment on the quark-gluon plasma. We have key advances in the heavy flavor sector, a new regime of J-side production dominated by recombination of charm quarks, which we can use as a calibrated Brownian probe, and we are really getting into the quantitative study and measurement of the QGP parameters. We have collectivity in small collision systems, and this gives new opportunities. We can use the tools, the PTAs and the Herwigs that have been developed over so many years to tackle the microscopic behavior, the microscopic way in which the QGP transition behaves. We can explore the turn-on of collectivity essentially by tuning the multiplicity in our collisions, and the high statistics, high precision era for this physics is about to start. Thank you very much.
Thank you very much indeed.
Sorry for keeping you. I think you will enjoy your lunch.
Not at all. Thank you very much for compressing your presentation somewhat. But I think it's only fair to take a question or two from the audience, and particularly, if you don't mind, from the students. We haven't heard a word from any student yet. I think that would be appropriate. I'm afraid you'd have to come down to the